application of the multiplication rule to dependent events. Welcome, everyone. In our previous lessons, we spent some time building the theoretical foundation of the multiplication rule, learning the basic mechanics of how probabilities interact. Now, we are going to take those concepts and move beyond the theory to explore how we can apply this rule to real-world scenarios. Specifically, today's focus will be on what we call dependent events. This is a crucial concept where the outcome of the first event actually changes the probability of the second event occurring. As we move through the next few slides, pay close attention to how that change in probability affects our calculations. Understanding dependent events. Now that we have established the theoretical foundation in the previous slide, let's dive deeper into what it actually means for events to be dependent. Essentially, we say two events are dependent if the outcome of the first event directly affects the outcome of the second. Think of it as a chain reaction where the first result changes the landscape for what follows. A classic real-world example of this is a process called sampling without replacement. To visualize this, imagine you are selecting an item from a group, like a marble from a bag, and once you've picked it, you do not put it back before making your next selection. Because that first item is gone, the total number of available items, which we call the sample space, decreases. Because the sample space has changed, the probability of the second event is no longer the same as it was initially. It is now conditional upon exactly what happened during that first event. This brings us to the specific step-by-step method we will use to solve these types of problems in the next slide. Step-by-step process for solving dependent event problems. Now that we understand what makes events dependent, let's walk through a reliable, step-by-step strategy you can use to solve these problems every single time. First, you need to identify your first event, which we will call E. Your goal here is to determine the probability of this first event occurring, looking only at the initial state of your sample space. We represent this probability as P of E. Second, this is the most critical step. You must update your sample space. I want you to mentally assume that event E has already happened. Because we are dealing with dependent events, like the without replacement scenario we discussed in the previous slide, you must adjust both your total number of possible outcomes and your number of favorable outcomes to reflect that the first item is now gone. Third, identify your second event, which we denote as F given E. This is what we call conditional probability. You are calculating the probability of event F occurring, specifically under the condition that event E has already taken place. We write this as P of F given E. Finally, once you have both pieces, you apply the multiplication rule. You simply multiply the probability of the first event by the conditional probability of the second event. In mathematical terms, the probability of E intersection F equals P of E multiplied by P of F given E. We are going to put this exact four-step process into practice in the next slide using a marble drawing example, so pay close attention to how the numbers change in step 2. Real-world example, drawing marbles from a bag. Now that we have established the theoretical framework, let's move on to a practical application to see how this works in a real-world scenario. Let's look at this scenario. Imagine we have a bag containing 5 red marbles and 3 blue marbles. We are going to draw 2 marbles, one after the other, and importantly, we are doing this without replacement. This means the first marble is not put back into the bag before the second draw. Our objective is to calculate the probability that both marbles drawn are red. To solve this, we will follow a structured, step-by-step approach. Step 1. First, we must define our events clearly. Let's let event E represent the event that the first marble drawn is red, and let event F represent the event that the second marble drawn is red. We are looking to find the probability of event E intersection event F, which represents the probability of both events occurring. Step 2. Next, we calculate the probability of the first event, which is the probability of E at the beginning. We have 5 red marbles and 3 blue marbles, which gives us a total of 8 marbles in the bag. Therefore, the probability of event E or the probability of picking a red marble first, is 5/8. Step 3. Now, this is the critical step when dealing with dependent events. We must update our sample space. Because we are drawing without replacement, we assume the first event was successful, meaning a red marble was removed. Consequently, the composition of the bag has changed. We now have only 4 red marbles remaining, and the total number of marbles in the bag has decreased to 7. Step 4. Now we can identify the second event, specifically the conditional probability of F given E. This is the probability that the second marble is red, given that the first marble drawn was red. Based on our updated count, this probability, written as P of F given E, is 4/7. Step 5. Now, we apply the multiplication rule that we learned in the previous slides. We multiply the probability of the first event by the conditional probability of the second event. So, we take the probability of E, which is 5/8, and multiply it by the probability of F given E, which is 4/7. This calculation gives us 20/56. Step 6. Finally, we simplify our result to reach the final answer. The fraction 20/56 can be simplified by dividing both the numerator and the denominator by 4, giving us a final probability of 5/14. As we move to the next slide, keep this process in mind, as we will discuss some common pitfalls where students often forget to update these values correctly. Common mistakes to avoid. First, watch out for forgetting to reduce the denominator. This is perhaps the most frequent mistake students make. When you are working without replacement scenarios, like we saw in the previous slide, the total number of items in your sample space must decrease. You cannot keep the total number of outcomes the same for both events. For instance, you shouldn't use 8 as the denominator for both draws. Remember, the denominator must decrease by 1 for the second event to reflect that one item is now gone. Second, be careful not to forget to reduce the numerator. This happens specifically when the second event involves the same category as the first. If we are looking for the probability that both marbles are red, and you have already successfully drawn one red marble, the number of favorable red outcomes must also be reduced by 1. If you don't adjust the top number of your fraction, your probability will be inaccurately high. Finally, avoid the mistake of treating dependent events as if they were independent. Do not simply multiply the probability of event E by the probability of event F using their original starting values. If you do that, you are ignoring the dependency. Instead, you must use the conditional probability, which we write as the probability of F given E. Now that we have worked through our marble example, I want to pause and discuss some common pitfalls. Even when you understand the concept, it is very easy to make small computational errors that change your entire result. As we move to our final slide, keep these warnings in mind to ensure your logic remains sound throughout the entire process. Key takeaways. All right, we have reached the end of our lesson. Let's take a moment to recap the key takeaways from today's session to ensure you have a solid grasp of the material before you move on to your practice problems. First, let's revisit the concept of dependency. Remember, we say events are dependent when the outcome of that very first event actually changes the probability of the second event occurring. It's that connection between the first and second steps that defines dependency. Second, keep a sharp eye out for the phrase, without replacement. Whenever you see this in a word problem, it should act as a red flag or a key indicator. It tells you immediately that you are dealing with dependent events and that your sample space, the total number of items available, is shrinking as you progress through the experiment. Third, let's solidify the formula. For these dependent events, the joint probability, which is the probability of both event E and event F happening, is always calculated as the probability of event E multiplied by the probability of event F, given that event E has already occurred. In mathematical terms, we write this as P of E intersection F equals P of E times P of F given E. Finally, I want you to focus on using sequential logic. Don't try to jump straight to the answer. Always follow this 3-step mental checklist. First, calculate the probability of the first event. Second, update the conditions of your experiment to reflect what has changed. And third, calculate the probability of the second event based on that new state. If you follow this logical flow, you'll avoid the common pitfalls we discussed earlier. Great job today!